Okay, hello all. We're starting the notes that you will need for tomorrow. We're still in section 2.5, and as you remember from class, we sort of ended on the fact we have the Fibonacci sequence. And so what I would advise you to do is to pause and pause and copy everything on this page and then play and then listen to the video and on the next page as well. And then I think from there on I'm going to write as I talk. But for the first 2 pages I actually just wrote it down in advance to save time, and then I'm gonna go over it. So here, the Fibonacci sequence, we see that it's f sub 1 equals 1, f sub 2 equals 1, and then we have the formula f sub n plus 2 equals f sub n plus 1 plus f sub n, where n is greater than or equal to 1. Now, because of the proof that we're going to do, you need to keep in mind the second fact is that if for n larger than, greater than, or equal to 3, so if we're starting from 3, then it's actually the formula f sub n equals f sub n minus 1 plus f sub n minus 2. And as you can see, all we did is subtract 2 from the indices, from the subscripts, in order to get this new formula. So they're the same formula, but the second formula is when we have when n is greater than or equal to 3. Okay, and so our example 3 will be, let alpha be the positive solution to the equation x squared equals x plus 1. And so alpha is equal to 1 plus the square root of 5 over 2, which is about 1.618. And some of you that number might look familiar to some of you. If not, that's okay. And so what we need to prove is that f sub n is less than or equal to n plus 1 for all n greater than or equal to 1. Okay, and so in other words, let's define our set. So when we're doing this, it's going to be a proof by induction. And when we define our set, we have S equals N. Actually, we don't need to define this set. So we can, because I think I did it a different way. Yes. So we are going to erase. So I hope you're writing in pencil or have some whiteout. And so we're going to prove that f sub n is less than or equal to alpha to the n minus 1 for all n greater than or equal to 1. Okay. So again, you might want to stop this page, copy this down, and then play the video. Okay. So we're proving this. Now, if we look over here, we're trying to prove f sub n is less than or equal to alpha to the n minus 1. So it looks like we're going to need this form of our Fibonacci sequence number. And so in order to use that form, though, n has to be greater than or equal to 3. Well, what can we do? Since n is greater than or equal to 1, all we need to do is show that it works for 1 and 2, and then we can use that formula for anything greater than or equal to 3. So I hope that makes sense. All right, so here, for n equals 1, so for n equals 1, f sub 1 we already know is 1, right? So that's a given to us. And then, so that's the left-hand side of that inequality. And the right-hand side, alpha to the 1 minus 1, well, alpha to the 1 minus 1 is just alpha to the 0 power, and that's 1. So thus 1 is less than or equal to 1. So we just showed it worked for 1. Okay. And then for n equals 2, well, f sub 2 we know is 1. And then I'm missing something here. What am I missing? Alpha to the 2 minus 1 equals alpha to the 1, which is about 1.618. So there again we have 1 is less than or equal to 1.618. Okay, so now let n belong to the naturals and n be larger than or equal to 3, because we just showed for 1 and 2 it works. So now we can just assume for n larger than or equal to 3. Suppose, and here I think early in the course someone asked about in terms of induction, like does it matter if we change our variable? It actually will make a difference here. Because of what we're trying to show, we can get confused. So it's really going to make a difference here. And so in general, like I said, you can always change it to, a K or M or some other variable so you won't get confused. In some instances, you don't need to change it to show, like in that first example we did. But in this example, it's going to be important that we change it. So let n belong to the naturals and n is larger than or greater than or equal to 3. Okay. And suppose f sub k is less than or equal to alpha to the k minus 1 for all a 1, 2, 3, all the way up to n minus 1. So that means we're going to be using our principle of complete induction, what we learned in class, to solve this proof. And so we need to show that f sub n is less than or equal to alpha to the n minus 1. Okay, so let's start. Let's continue on. And so let me go back. Yes. So we need to show that. So, oh, we don't want that. Okay. So that would mean, so similar in terms of when we're doing induction, we start from the left side to prove the right side. So the left side of that show part is our f sub n, right? Well, we know since n is greater than or equal to 3, we know f sub n equals f sub n minus 1 plus f sub n minus 2, right? Okay. And from there, we can say then that this, since n minus 1 belongs to our, is a subset of our set, or it belongs to k, right? It's k is one of those choices, and n minus 2 is also, right? Because we suppose, let me go back. So what I mean is right here, okay? Right here, we're supposing for every k, again, less than, up until n minus 1, then this statement right here holds true, okay? And so so that means for up until that's true. So then we can say that means that this is less than, oh, I keep going to highlighter. So this would be less than or equal to what? Alpha to the n minus 2 plus alpha to the n minus 3. And this is by the induction hypothesis, right? Or by our supposition. Okay. And I'm keeping track of our time as well. Okay. So now this, so we have, this is less than or equal to alpha to the n minus 2 plus alpha to the n minus 3. Well, let's see, where can we go here? Let's see, can we factor something out? Okay, so then we kind of think about things. Well, this equals alpha to the n minus 3 plus 1 plus alpha to the n minus 3.